In this lecture, we're going to be talking about probability. These are the things we're going to cover. First, we introduced the idea of probability. What actually is it? Then we talk about populations and samples. Basically, we're going to introduce the idea of inference. Inference meaning how do we use the conclusions we get from our samples to infer or to make a conclusion about something about the overall population. Then we will talk about random variables, what is this randomness in the first place, and probability distributions. Now some starting thoughts. Let's look at this statement. People who smoke have a high probability of developing cancer. Now you might be thinking, is this claim actually valid? Like it says here people, does that mean everyone? And how do they know that? If everyone who smokes have a high probability of developing cancer, that would imply that I have tested everyone by telling everyone, please smoke and see whether they have a probability, and see whether they have a tendency of developing cancer. And of course, the question is, this probability word, what actually does it mean? So let's start by looking at the word probability. It comes from the root word probare, Latin, means to prove or to test. Now we don't usually use the word probability in our daily lives. More commonly we use stuff like chance or likelihood, certainty, odds. They, technically speaking, they mean different things, but they're interchangeable in our common language. Now the idea about probability is this. Let's assume we have an experiment, and we can repeat this experiment multiple times, and each time we repeat it, we call it a trial. So we do it once, it's one trial, twice, two trials, and so on and so forth. So the probability of any given outcome is the number of occurrences over the total number of trials. Now simply speaking, let's say I have a coin with heads and tails. Those are two possible outcomes. So, and I flip the coin once, I call it a trial. So I flip the coin 10 times, that will be the total number of trials. How many times do I get hits? That would be the number of occurrences. So let's say I get hits 5 times out of a total number of 10 trials, so the probability would be 5 over 10, which means half, or 50% of the time. Now how do I determine what was the probability of that coin, or for any other situation in the first place? There are basically two ways you can go about it. The first way is to determine the probability empirically, also known as experimentally, or via theoretical models, or in theory. Now, take for example, let's go back to the coin again. A theoretical model would be me telling you that I have a perfect coin. A perfect coin means the head and the tail side are exactly the same weight and exactly balanced, and it's totally uniform. When I flip the coin and it spins up into the air, it's totally random. There's no way I can predict what side is going to come out from. So, using this theoretical model, what's the probability of getting hits? Well, theoretically it would be 50%. Now, empirically, on the other hand, would be me flipping the coin, let's say 50 times, 100 times, and then just calculating the total number of hits after the total number of trials. Now, the nice thing about empirical methods is that you don't have to come up with a theoretical model. You can just test it straight away. Now, the problem, of course, with empirical models is that, let's say I toss the coin once, come out hits. Now, does that mean that the probability of getting hits is 100%? Obviously not. Because if I flip it 10 times, it's going to be different. And if I flip it 10 times, what's the chance of me getting exactly 5? Also, well, not necessarily 100% either. If I flip it 1,000 times, 10,000 times, and so on and so forth, sooner or later, the larger the number of trials I do, the closer my empirical solution is to the actual theoretical one. Now, the formal concept of probability is this. I've been talking about percentages per probability, but in truth we actually use real numbers between 0 and 1. Real numbers meaning numbers with decimal points inside them. So the smallest probability is 0, and this is an impossible event. A probability of 0 means it's never going to happen. This outcome will never happen. Then you have a probability of 1, which means a certain event. It's definitely going to happen, meaning there's a probability of 1. No matter how many trials I do, in every single trial I will get the exact same outcome. Now the closer the probability is to 1, the more likely it is to occur. So for example, let's say I have a coin which is not fair, and this coin has a probability of 0.9 for heads. So that means that every time I flip it, I have a 90% chance it's going to come out heads. If I flip it 10 times, chances are I'm going to get 9 heads. All possibilities add up to 1. This means that for a particular trial, if there are 2 outcomes, then each outcome of a probability, but both of these outcomes added together will become 1. So for example, a given trial for flipping a coin, there's heads and there's tails. Let's say it's 50% for heads, 50% for tails. Both of them add together is 100%, or 0.5 plus 0.5 equals 1. Now alternatively, it could be a dice, a 6-sided dice, and each probability of turning up one side for a fair dice would be 1 over 6. So you add all these probabilities together, 1 over 6 plus 1 over 6 plus 1 over 6 plus 1 over 6 plus 1, and so on and so forth. It adds up to 1. It must add up to 1. Let's continue to look at probability. This time, let's look at the definitions and rules. And once again, something to think about. What we are doing in this case are experiments. And experiments are planned process of data collection. We're collecting data. And how should we do this data collection? It should consist of a number. Of course, that means that we have to do quite a few of them. You can't just do one. Of independent trials. Remember what are trials? These experiments, what we are doing. And independent here means as we do these multiple trials, each of these trials should have no impact on the other, meaning the outcome of this trial should have no influence on this trial, should have no influence on this trial. Meaning, let's say measuring that smoking cancer one. If the outcome of this patient was that he had cancer, I cannot carry that bias with me to the next patient and says, oh, definitely he's going to get cancer, and then I see this guy also has cancer, I say, oh, definitely he has cancer, and so on and so forth. It should be totally independent, meaning that I treat each trial as a totally separate object. However, they should be done under identical conditions, meaning if I'm doing this trial for let's say a patient of age 30, then the next trial should also be of a patient of age 30, and the next trial and the next trial, and if I'm testing him in this room, I should also do it for this room with this instrument, and so on and so forth. Identical conditions. Now this is our method of notation for probability, meaning that when we want to say the probability for a given outcome, let's say x, let's say heads for example, then we will use this p bracket heads or p bracket x or something like that. Now remember the rules once again. Probability is a number from 0 to 1. There's no such thing as a negative probability. So every possible outcome should have a probability that's 0 or greater. And the sum of our probabilities should equal to 1. So in this case, here's a table here. There are 2 sets of outcomes in this case, notice. It's possible to have blood types. There are 4 outcomes here for blood types. So you can have a blood type O or A or B or AB, but nothing else, right? And also you can be male or female, but nothing else. And the probabilities of being male is half, probabilities of being female is half, and so you add these 2 together, you get 1. Similarly, the probability of you having a blood type O is 0.42, probability of blood type A is 0.43, B is 0.11, probability of the blood type AB is 0.04, and once again they all add up to a probability of 1. Now keeping that in mind, let's take a look at the notation here. Let's say I'm asking myself, what's the probability given this kind of data here? This is experimental data. Given this data here, what's the probability of me or any random person being of type A blood type? So let's have a look. So type A blood type, what's the probability for any random person? It's 0.43. So that's the answer here. Now, what's the probability of you being not, of any random person being not type A? Now you could say the probability of being not type A, you just look at all the other outcomes. So that's O, that's B, that's AB, and you just add them together. So probability of O plus probability of B plus probability of AB. Or else you could do a shortcut, and you know that all of them add up to 1. So the probability of not blood type A would just be 1 minus the probability of A. And there we have it here. The answer should come out to be exactly the same, assuming of course that you have the full list of outcomes here. Now let's talk about something called mutually exclusive events. This means that two or more events are mutually exclusive if the occurrence of one event precludes the occurrence of the others. Now, this just means that if one occurrence happens, the other occurrences or the other outcomes will not happen anymore. Now, if you remember the table just now, let's talk about blood type, for example. Now, you can be blood type O, but if you're blood type O, you cannot be blood type B, AB, and so on and so forth. If you're blood type A, you cannot be blood type O or B or AB. So this blood type is mutually exclusive. You can be one, and once you're one of them, you cannot be any of the others. Similarly, you can be male, but you cannot be female at the same time that you're male. Or you can be female, but you cannot be male at the same time where you're female. Okay, I know this sounds a bit confusing. It just means only one of the outcomes can occur at any one time. Now, usually, mutual exclusion is designed into an experiment by definition, meaning this is something that's kind of built in. So for example, let's look at this table again. This is a mutually exclusive outcomes. Let's say we're talking about heights. Now, you can be from 150 to 160, or from 160 to 170, 170 to 180. If you're 175, you're in this group and you cannot be in the other two groups. So these are mutually exclusive. However, you could also define your outcomes to look like this. It could be below 150, it could be below 160, it could be below 170. That means if your height is, let's say, 140, you will be in all three groups at the same time. And this obviously is not mutually exclusive. And usually we want mutually exclusive events because quite a lot of our statistics depend upon one of the criteria being mutual exclusion. Now, if your events are mutually exclusive, then the probability of either one or another event occurring is the sum of the probabilities of both events. Meaning that if you want to know the probability of me being one outcome or another outcome and so on and so forth, you can just add them together. Now, we actually did that just now in the first table. Remember, we said, what's the probability of you being not type A? I mentioned you could calculate that just by checking the probability of type O plus type B plus type AB, and you added them together. Now, we did that very naturally because we've done that before, I'm sure, inside your secondary school. But one thing to keep in mind is this thing only makes sense if your events are mutually exclusive. If they are not mutually exclusive, this so-called addition rule does not apply. Now, in the previous slide, we talked about something called mutually exclusive events. Now, let's introduce something called independent events. Now, two or more events are independent events if the outcome of one has no effect on the outcome of the other. Now, previously when we talked about mutually exclusive events, it usually referred to within the context of a particular variable. For example, blood type. If I am blood type O, at the same time I cannot be blood type A. If I'm blood type A, at the same time I cannot be blood type B, and so on and so forth. So these are mutually exclusive. Now, similarly, when we talk about gender, I can be a male, but at the same time I cannot be female, and vice versa. Now, we talk about crossing between or the combination of two variables, then mutually exclusiveness doesn't really apply in this case. So, for example, I can be male and type O, and I can also be male and type A. I can be A and female and O and male and O, and so on and so forth. However, we can talk about something called independence. Now, what this basically means is that whether I am male or whether I'm female will not have any effect on the probability of my blood type. Or in other words, my gender has no effect on my blood type, and my blood type has no effect on my gender. Or put it yet another way, if I am male, the probability of me having a blood type of O is the same as if I am female, and the probability of me having a blood type of O. Now, ignore the numbers inside here for the moment and just focus on the totals over here. Independent events mean that if these two events here, gender and blood type, are independent, it would mean that my probability of me being a male having a blood type of O would be 0.42. And my probability of me having a blood type of O if I was female is also 0.42. And the same thing applies in reverse. If I'm a blood type of O, the probability of me possibly being a male is 0.51. If I know I am blood type of A, the probability of me being a male is also 0.51. And if I know my blood type is B, my probability of being a male is, yes, also 0.51. This is only true if these two events are totally independent from each other. Now once again, this means that independent events means that if I am one of the outcomes in one of the events, it has no influence on the outcome of the other event. Now if the independent clause is true, meaning for independent events, then we can calculate the probability of both events occurring together at the same time. And that would be the multiplication of the probabilities of both events, meaning that if I am male and type O, then my probability of that is the probability of me being male and the probability of me being type O multiplied by each other. So in this case it would be 0.51 multiplied by 0.42. This so-called multiplication rule once again is only true for independent events. Now that we know the multiplication rule, let's introduce the concept a bit further, which is the concept of joint probabilities and marginal probabilities. Now these are the so-called marginal probabilities and these are the so-called joint probabilities. Now this only makes sense when you have more than one variable, meaning they have two variables inside here. If you have only one variable, then there's no such thing as joint or marginal probabilities. Now, you probably have noticed by now that the marginal probabilities are the probabilities of one particular variable. So for example, the marginal probabilities here are for blood type. The marginal probabilities here are for gender. Joint probabilities then is kind of like the multiplication rule. The joint probability means what's the probability of me being the outcome of one variable and the outcome of another variable at the same time. So the probability will be male and type O, in this case, is 0.2142. Now if you remember, that's exactly the same answer of what we got just now when we were trying to calculate using the multiplication rule. And how did we use the multiplication rule? It was if I am male and type O and that these two variables are independent variables from each other, then it would have been the probability of male 0.51 multiplied by the probability of me type O. These are both the marginal probabilities, multiply them together, and that is my new probability of being these two outcomes at the same time. This would be the joint probabilities. So knowing the multiplication rule just now, knowing the concept of independence, if two events are independent, then their joint probabilities, all of them here, must equal to be the product of their marginal probabilities. Now this is just another way of stating the multiplication rule. It's also a way of testing to see whether the data you are given is actually independent from each other. If this variable is independent from this variable, then this thing here must be true, meaning the joint probabilities here must equal the product of their marginal probabilities. If they do not equal each other, then these two variables here are no longer independent, and unlike mutual exclusion, non-independent variables are actually quite common. Now let's consider what happens for a case where the two variables are no longer independent, they are non-independent. So keeping that in mind, it should be clear that if you take the marginal probabilities here and you multiply the marginal probabilities, you do not get the joint probabilities inside here. Rather, the marginal probabilities here is just the sum of the rows or the sum of the columns in this case, right? So I'll just repeat that. This is a non-independent case. The data inside there has changed compared to the previous table, and so whether you're, let's say, whether you're male or female will affect the probability of you having a blood type, right? Now compare it to the previous one. So the multiplication rule no longer works. Now in this case, finding out the probability of you being male, it's no longer probability of you being male and being type O, in this case not type O. Now it's called probability of you being male given that you are not type O, right? So this is called conditional probability. It's a separate thing. Now the idea here, if you want to calculate this out, the probability of you being male given that you are not type O, how it works it's basically something like this. First you got to calculate two things. First you got to calculate given that you are not type O. Given that you are not type O means you're either one of these three, A, B, or AB. And the probabilities of that, since they're mutually exclusive, is just 0.433 plus 0.057 plus 0.07. So that's the denominator here. Now for the numerator here, that's the probability of you being male. Now by you being male, it's not 0.51 here. It's probability of you being male given that you are already not type O. So you erase this part, so it's this part. 0.218 plus 0.032 plus 0.050. So I'll just repeat that. The probability of you being male, given that you are not type O, is equivalent to the probability of you being male here over the probability of you not being type O. Now notice the cross section here, and notice that this is not the same as calculating the probability of you being male and not type O if this was a independent variable. If this was an independent variable, it would just be a multiplication of the marginal probabilities. Keeping in mind that what we did just now, let's introduce non-independent multiplication. If two events are non-independent, their joint probability is the multiplication of the probability of one and the conditional probability of the other. Now remember, when we were working with independent variables, if we wanted to calculate the probability of you being male and not type O, it was just probability of male multiplied by probability of not type O. But that's only true if it's non-independent. That's only true if it's independent. If you have non-independent variables, then to get this same thing, you would have to multiply the conditional probability multiplied by the probability of the second variable. So in other words, instead of probability male multiplied by probability not O, it will be probability male given that you are not type O multiplied by probability of not type O. Right? Other than that, it's pretty straightforward. Now if you look at this, the non-independent multiplication formula, you may notice that this is actually just a rearrangement of what we did in the previous slide. The previous slide, we're trying to calculate the conditional probability, and I remember I told you the conditional probability was based on the numerator over the denominator, where the denominator was just the probability of you not being type O. Well, that's here. Notice it just gets shifted down, and the numerator, the one on top, was just the the joint probability of you being male and not type O, meaning that you are male and you're also not type O, and that was those three probabilities in the table just now over the three probabilities of you not being type O. So again, this equation here really is just a rearrangement of what we worked out just now for conditional probability. Now as you can probably guess, just now when we were looking at mutually exclusive addition, the addition rule just now, there's also non-mutually exclusive addition. What happens when you want to calculate the probabilities of two possible events occurring when they are not mutually exclusive? Now when they are mutually exclusive, it was straightforward. Probability of male or type O would have just been probability of male plus probability of type O. Now if they are not mutually exclusive, you can't do this anymore, and that should be quite obvious, because if you try to use the same sum, it is quite possible to end up with a probability that's bigger than 1, right? So the only difference here is you still do the sum of the probabilities, but you have to take away the probability that both occur at the same time, right? So probability of you being male or type O equals probability of male plus probability of type O minus the probability of male and type O at the same time. Once again, it's straightforward. And notice one thing, this equation here can fall back to the standard equation for events which are mutually exclusive, meaning that I can use the same formula for mutually exclusive events, because in mutually exclusive events, the probability of these two events occurring at the same time is 0, right? Because that's what mutually exclusive means. It means they cannot occur at the same time. So the probability of them occurring at the same time is 0. So in other words, you're left with just the first two, which brings us back to the addition rule in mutually exclusive events. So here's a quick summary of the rules. if you have mutually exclusive events, and you want to ask what's the probability of this or this or this occurring, then it would just be the probability of A plus B plus C. Now you have non-mutually exclusive events, then the question you would ask is what's the probability of A or D occurring? It would be probability of A plus probability of D minus the probability of A and D occurring at the same time. Now if you have independent events, then the question you might ask is what's the probability of A and B and C occurring at the same time? And for independent events, there will be A multiplied by B multiplied by C. If they are not independent, however, then what is the probability of B and D? It would be the probability of B given D, or the conditional probability of B, D, multiplied by probability of D. Okay, and similarly, this can be switched around. So this one and this one are actually equivalent. You can work that. You can try that out using the table just now and see whether that is true. Now let's look at the concept of population and samples. First, population. A population is a set or collection of items with something in common. For example, a population may be a definition where all male smokers which are bigger than 50 years old. Right? Now notice that this male smokers above 50 years old, if I add no other conditions, this naturally applies to the entire population which matches this criteria, meaning male smokers above 50 years old doesn't matter their race, doesn't matter where they live, right? And maybe doesn't even matter in what era which they ever lived, right? So in other words, this thing would apply, this population of male smokers above 50 years old would apply to American smokers, would apply to Chinese smokers, would apply to British smokers, Australian smokers, and so on and so on. It would apply to people who are 100 years old, even 150 years old, and so on and so on, as long as I've given the definition of what this particular population is defined as. Now, in contrast, a sample is a subset of the entire population which we defined earlier, and is selected to be representative of the overall population. Now what this means is, obviously, male smokers above 50 years old, this is a huge population. Keep in mind that, as I said here, this could be for the entire world. But having said that, let's just restrict this now. Male smokers in Malaysia above 50 years old. Now even then, that will probably easily get us at least, let's say, 1 million people. Now if I wanted to collect data about this 1 million people, it's not feasible at all. So rather than collecting data about all of that 1 million, I take a sample, meaning I pick out of the 1 million maybe just 1,000 of them. And I assume that the 1,000 people that I selected, this subset of people, this sample of people, this 1,000 samples, they are representative of the overall population, meaning that they are I can use this 1,000 people and make some conclusions about the population at large just based on this 1,000. So that is what a sample is. In practical sense, we always measure a sample, and we use the sample to make conclusions. The correct term is inferences about the population as a whole which we are targeting. Now, sampling is faster and cheaper, that's obvious. And it may be impossible to study the entire population in the first place. How would I actually go around collecting all the male smokers in Malaysia above 50 years old? It's probably quite it's probably quite infeasible. Given that I have to sample, or that sampling is really the only practical way to collect data, the goal here is that whatever samples which I collect should be representative of the population, or should reflect the population, meaning that I should be collecting 1,000 of typical patients above 50 years old who smoke, or the typical patient in case of whatever else I'm trying to measure. The requirements for sampling, it should be independent, it should be fair, it should be non-biased. Fair and non-biased usually are quite related. Independent means that each and every one of the samples which I pick, they have nothing to do with each other, meaning that this guy here does not know this guy here, does not know this guy, he's not influencing, there's no influence upon each and every one of them. Non-biased means I did not just pick, I picked the 1,000 most healthy smokers or the 1,000 most sick smokers. Okay, they should be non-biased. And how should I fulfill these requirements for independence, fair and non-biasedness? I should use random selection. You probably have some idea about the word random here, usually taken to mean unpredictable or without pattern, without discernible pattern. In this case, we just say there is no bias inside here for what random sampling is. And so how do I go about it? Now, there are some ways I can do. Simple random sampling. Let's say the population has 1 million people, so I want to pick 1,000 from them. So each of the 1 million people, there's an equal chance of getting selected. So I generate, let's say, random ID numbers here might be, out of that 1 million people, I have 1 million of their IC numbers. And so I randomly pick 1,000 of them. So there's an equal chance that of any of those million to get picked into my sample. This is probably one of the best ways of doing it. Systematic sampling, on the other hand, is like selecting each case item. So in other words, patients come into the hospital, rather than selecting all of them because there are too many, I select every 10th patient, the 10th one, 20th, 30th, 40th. This one's not as good as simple random sampling, but you can probably see why you would pick this one, because it's easier to carry out, easier to manage. Stratified sampling is where you first divide the population into groups, and then you sample randomly from each group. This is if you want to control for certain variables. Now, say for example, just now I was talking about smokers above 50 years in age. And then I wanted to say that, but when I sample, I want to have equal numbers of males and females. But it so happens that in the population as a whole, there are more male smokers than females. So first I would group them into males and female smokers. Then I would sample 500 from this group and sample 500 from that group. So that's stratified sampling. I break them into groups first. Right? Cluster sampling is very similar to stratified sampling in the sense that they're also divided into groups of some kind. However, cluster sampling is usually based on geographical division rather than on about the patient's properties themselves. So in this case, let's say if you look at the map of Malaysia, if I'm trying to measure something about Malaysians in general, there's a problem. There's a large concentration around the major cities, for example, Kuala Lumpur, Penang, and Johor. So if I try to make a random sampling, it'll be quite biased towards the larger cities. So what I could do is first I break them into states, and then within those states, then I sample a certain number. So I will restrict, in other words, force equality between the different locations. So this is to equalize for population density. So keep in mind that population and samples here is really about practical compromises. If you had infinite money and infinite time and infinite manpower, then you would try to measure the entire target population which you're interested in. So for example, let's say I'm trying to do some kind of study about a particular drug that's targeted towards cardiac patients in Malaysia. So if I had infinite time, infinite money, I would measure all of them out, test all of my target population. Now in reality, I can't do that, so I pick a sample. So the sample would be the population where the sample is taken from, in this case cardiac patients in University Hospital, and from there I measure the actual sample data. So my sample data here comes from my sample population, which is supposed to be assumed to be representative of my target population. So the data that I generate over here, at the end of the day, I'm going to say that if I did everything correctly, if it was random, it was non-biased, it was independent, it was fair, and there's enough numbers inside here, then the data I generate here is representative of the target population as a whole. So knowing that there are populations and samples, so you can probably guess that you can calculate the population mean as well as the sample mean. For example, the population mean, will you be calculating the mean of the entire 1 million members of the population, and the sample mean, will you be calculating the mean of only that 1,000 samples. Similarly for correlation, standard deviation, proportion, so on and so forth. So as expected, there are also different symbols used to represent different things. In population, we usually use the Greek alphabets. So in other words, mean here is mu, correlation here is rho, standard deviation is sigma, proportion is pi. In samples, the sample values on the other hand, mean is x bar, correlation is r, standard deviation is s, proportion is p. Right? So these are just the symbolic differences. Let's look at some terms which we've been using up to now without actually defining them in specific. Now the first one is variable. We've been using that a lot. Now, variable, as you probably can guess, it just means a characteristic of interest in a particular study, or in other words, it's a measurement. It's one of the measurements. It could be the age measurement, it could be the blood type measurement, it could be the gender measurement, etc., etc., etc. That's just what a variable is. Now, a random variable is the same thing. It's also a variable, characteristic of interest, except it has been measured randomly, meaning you assume that this variable has been measured without bias, has been fair, has been non-independent, and everything we talked about previously. A probability distribution, then, is a frequency distribution summarizing the values of a random variable. Now, meaning, remember what we talked about a distribution? A distribution is like a histogram. That's the shape of the histogram, where the x-axis were the different values, the possible values you could get, and the y-axis was a frequency, or the number of occurrence, how many times something could occur for every particular value. Probability distribution just replaces the y-axis, the frequency or the count, with the probability values, which just means that it is restricted to from 0 to 1. 1 being it happens all the time, and 0 means it never happens. Up till now, when we talked about distributions, I'm just going to use the term probability distributions from now on. We've kind of assumed that we could only generate a probability distribution based on empirical data, meaning based on me going out and measuring 1,000 samples, then creating a histogram based on the values and based on the frequencies, and voila, I have my distribution here. And of course, I could change that into a probability distribution just by converting frequency into probability values. Now, that's not the only way. Just like just now, way at the beginning, remember we talked about probability. How could I calculate probability? One way is by empirical. The other way is by theoretical. So in other words, now I'm saying here that it is possible to create a probability distribution that is simply based on a formula, that's based on a theory. Now, what is a distribution? Again, it is like the histogram that has a shape. As you can probably imagine, I could define any shape I wanted. For example, I could have a formula that defines out a distribution that is rectangular. And voila, I could call it the rectangular distribution. And it is not based on me going out and measuring data. I'm just saying that I have a distribution where the outcomes, the possible outcomes are on the x-axis, and the expected probabilities are on the y-axis. And I expect it to look like this if I were to go out and actually measure it. Similarly, instead of a rectangular distribution, perhaps I would say I have a distribution that I think will look more like a mountain, will look more like a bell curve. And this bell curve is defined just based on a formula. And this formula, for example, says that if x equals what, then y equals this. If x equals what, then y equals this, and so on and so forth. And this formula would trace out the shape of a bell or shape of a hill. And I'll call this, let's say, a bell curve distribution. And I'll say that this bell curve distribution is not based on me going out and measuring it. I'm just saying that I expect if I were to go out and measure it, then the outcomes on the x-axis, the frequencies or the probabilities on the y-axis, if I were to go out and measure, would end up with a distribution that looks quite similar to this. Right? Now, it might interest you to know that many of the statistical methods that we are going to be using, we are actually assuming that the observed data represents a sample from a population with a known theoretical form. Now we are going to explore this idea in more detail later, and in fact this is probably one of the most important things to know, right? So once again, we'll talk about this again, but I'll just repeat this in another way. Many of the statistical methods that we're going to use, they have an assumption, and the assumption is that the data which you're collecting actually fits a theoretical distribution, the formula of a theoretical distribution. We are going to assume that your data, for example, fits a bell curve distribution, and based on that assumption, I'm going to calculate certain probabilities from it, right? I know the shape, and so knowing the shape, I can calculate some probabilities, and then I compare that to what I actually went out and measured. Did my measurements actually agree with what I hypothesized or what I assumed the original data would look like? Okay. Now again, we will approach this again many times, because this is one of the founding principles behind our statistics here. I'll just repeat again, many statistical methods assume that observed data represent a sample from a population with a known theoretical form. Probability distributions then. Our theoretical probability distributions, what do we use them for? Used to calculate the theoretical probability of different values and events, just like what I mentioned just now. If I have the theoretical form, I can use that theoretical form to calculate certain theoretical probabilities. And then using these theoretical probabilities which I calculated, I compare them to what I actually measured. Or I see whether these predictions or whether these estimates or whether these assumptions are actually true. And that actually represents one big chunk of what we are doing in statistics. Now let's look at some theoretical probability distributions. And we start with the simplest one, the binomial distribution. Now, binomial distribution is a discrete probability distribution. Just a quick reminder, discrete here means that the measurements that we get from the probability distribution, or the measurements that we get from measuring the data, is only in integers, meaning we can only measure like 1, 2, 3. For example, how many cases of cancer occurred in the hospital in the last month, maybe 5, maybe 10, but not 10.5 or 10.2 or 10.1. Now, the probability of frequency that a specified outcome occurs in a given trial in a given number of independent binary trials, this is what the binomial distribution is. And I'll just say right now, a lot of people, the natural assumption is that what does this distribution actually look like? They would think, okay, the distribution is the x-axis is the outcomes, right? And the outcomes here is this, since it's binomial, binary here means only 2. So the binomial distribution, there should be the 2 outcomes, so maybe yes and no. So the x-axis is yes and no, and the y-axis is the number of occurrences. So maybe yes was 20 and no was 10, right? Now that's kind of like, a lot of people, that's the natural assumption of what it should look like. But in this case, this is not what a binomial distribution looks like. A binomial distribution in this case rather is the x-axis is the possible number of outcomes, possible number of values for one particular outcome. So say for example, let's say I'm flipping a coin. Flipping a coin, there are 2 outcomes, heads and tails. Let's just focus on the heads outcome. Now the heads outcome, probability, if I flip a coin 100 times, right? It's a fair coin, chances are I get 50. So how would I plot that in the distribution? It would be the x-axis from 0 to 100. 0, 1, 2, 3, 4, all the way to 100. And the y-axis would be frequency or probability. Now what that would mean is that if I flip the coin 100 times, what is the probability of me getting 0 hits? What's the probability of me getting 1 hit, 2 hits, 3 hits, 50 hits, 80 hits, 90 hits, 100 hits? Okay, you're plotting out the frequency or the probability of each of the possible number of occurrences for a particular outcome, given a particular number of independent trials. So if I flip a coin 100 times, it can only scale from 0 to 100. If I flip a coin 50 times, it goes from 0 to 50. And you can probably guess that for a fair coin, the highest peak of whatever binomial, whatever distribution I draw is going to lie somewhere in the center. Now, given that this binomial distribution is a discrete distribution or discrete data, we can actually calculate the exact probability value for an exact outcome. So for example, if I wanted to calculate what is the probability of me getting 5 hits, x equals 5, given that I had 10 trials, n equals 10, n equals number of test data, and p, if this is a fair coin, probability of success for each data or for each outcome, so this would be 0.5 over here. I think you've seen this formula before. This n over k here is just calculating this particular value, the factorials, bringing them inside here, replacing it here, and just finishing off the calculation. And then I would be able to get the exact probability for the exact number of outcomes for the exact number of trials. This is only possible for discrete data. So let's take a concrete example. Let's say I'm trying to formulate a distribution where I'm measuring people with blood type B, where the probability of B is 0.08. Now notice here, since it's a binomial distribution, I'm not doing A, B, and O. I'm just saying people with blood type B or not B. Alright, just 2 possible outcomes. Now let's consider the case where we only collect two people, sample size of 2, so 0, 1, 2 possible outcomes over here. As you can see, if my probability of getting type B is 0.08, the theoretical probability which I calculated out inside there, right, this would be P x equals 0, this would be P x equals 1, this would be P x equals 2. I can calculate out the exact probabilities inside here. It will look like this. Now let's increase the sample size, n equals 10, and it still looks somewhat like a gigantic slope inside here, but once again I could calculate all the outcomes here, 0, 1, 2, 3, 4, 5, 6. Now it would actually continue on to 7, 8, 9, 10, but I didn't bother because 10 is tiny, it's negligible, you can't even see it. Now let's go to n equals 100, meaning that after collecting 100 people here, what is the probability of me finding 20 people inside here with blood type B? After collecting 100 people, what's the probability of me finding 10 people with blood type B? After collecting n equals 100, what's the probability of me finding people with 8 people with blood type B? And notice that n equals 100, if I take this n multiplied by this p over here, I get, what do I get? I get 8. And 8 so happens to be roughly around the peak of where I expect the number of people, or I expect to get the highest probability of finding this number of people. But I could also get 7, I could also get 9, and so on and so forth. Now the other thing I'd like you to notice is that, look at this shape here. It looks quite similar to a distribution that you have, you're quite familiar with. Perhaps it's the bell-shaped distribution. Now notice that this distribution, this shape, is going to crop up quite often, and there's a reason for that. We'll not get into that for now, but I'll just point out that this particular shape that I am letting you notice at the moment is extremely important in our statistics. Now let's continue to another distribution, the Poisson distribution. Now this is also a discrete probability distribution. Once again, discrete meaning only integers, no decimal points. So it's similar to the binomial distribution, where you have the probability or the frequency that a specified outcome occurs. So once again, the x-axis is also the occurrence, or the possible occurrences, and the y-axis is the probability or the frequency. Now the only difference here is that this Poisson distribution, now remember, this is a theoretical distribution. Just like the binomial distribution, this is theoretical. This is calculated by using mathematics. This is only used for rare events. This just means that when people were studying, they were studying how distributions fitted the real world. They found that for events that are rare, meaning events that do not occur very often, the Poisson distribution turns out to model actual rare events better than the binomial distribution. Which brings us to the question, what actually is rare? And unfortunately, that one, there's no specific criteria for what defines a rare event versus a non-rare event. Some people would say previously, the probability of you getting blood type B is 0.08. That might be a rare event as well. But this is something that is dependent, it's subjective. But anyway, other than that, the Poisson distribution is almost identical to the binomial distribution. Calculates the probability that an outcome occurs a specific number of times when the probability of occurrence is small, rare. Now, just like the binomial distribution, the Poisson distribution has a formula which allows you to calculate the exact probability for an exact situation, the exact number of occurrences. So in this case, let's say I wanted to know, let's go back to coin flipping one again. Although coin flipping is hardly a rare event, so probability of me getting hits would equal to be, probability of me getting hits 5 times, right, is equal to this particular formula here, where all I need to know to get the answer would be lambda and k, right? K happens to be the same k here, means 5. Probability of me getting 5 hits. So what's lambda then? Lambda is the mean and variance of the distribution, meaning that regardless of how, notice that what's missing here, what's missing is the n, right? The number of trials here is missing. So it's kind of like built into lambda already. So let's say I was flipping a coin 10 times, then my mean would be 5, right? Assuming it's a fair coin. Now, however, there's also the variance, meaning as I flip the coin 10 times, sometimes it'll be 4, sometimes it'll be 6, and this would be the spread, and this would be like the square of the standard deviation, if you still remember the previous lectures, right? Now if I know all this and my situation fits the need for a Poisson distribution, which I remind again, it does not fit for a coin flipping, because a coin flipping getting hits for a fair coin is not a rare occurrence, right? But assuming it does, then this is all you need to calculate out the probability for Poisson distribution. Now once again, we can consider some concrete examples. First, number of new cancer patients is in a day. So the mean and the variance is 2.2 here. And so once again, number of new cancer patients in a day is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Notice in this case, however, unlike the binomial, because I do not have a number of trials, there's theoretically no limit to how far this x-axis can go. After all, it is possible that in one day, suddenly 100 cancer patients suddenly showed up inside the hospital. It is possible. However, unlikely. So anyway, mean is 2.2, so notice that the peak is around 2.2. Number of visible stars in a section of the sky, mean is 8.4. Once again, you look at the peak here, it's around 8. Number of cars passing through road per day, this really probably no longer would be considered a Poisson distribution, but just for argument's sake, let's just show it. So 95.3, and so when we plot it, once again, x-axis is number of occurrences, and as you can guess by now, the peak is around 95, right? And again, look at the shape. Look at the shape that occurs, right, when the mean, variance, number of occurrences, whatever, becomes high, just like the number of occurrences for the number of trials for the binomial distribution went high. Once again, you are seeing this similar bell-shaped curve, this bell-shaped shape, right? It's going to occur many times. Which brings us to the normal or the Gaussian distribution. Now, unlike the previous Poisson and binomial distributions, this is a continuous probability distribution, and it's by far the most important distribution compared to the other two. Characteristic of its shape, this is the smooth bell-shaped curve which I've been hinting about all this time. There's one single peak, unimodal. There's only one model. A bimodal one would look like this. It is symmetric around the mean. So if it looks like this, and I draw a line in the middle, the left side and the right side would be identical. Keep in mind that symmetric around the mean, single peak, unimodal, smooth bell-shaped curve, these are all theoretical. They're theoretical distributions. This is a mathematical form. Now there are two parameters which define the entire Gaussian distribution. The first is the mean, which describes where is the center of the curve. Then there's the standard deviation, which defines the curve shape. Let's not call it the curve shape, but more like how narrow, or the width of the curve. So a small standard deviation would be a very sharp peak, a sharp and narrow peak, and a large standard deviation would be a short and wide peak. But these two parameters alone are enough to describe the entire of the standard of the normal distribution. Similar to the previous theoretical distributions, there is a formula to which defines this probability distribution, this normal Gaussian distribution. However, notice that unlike the others, this is an fx, right? And that's because this is used to point out that this is not a function. We are not calculating discrete values now anymore. This is not p or probability of x equals to k. This is talking about a continuous smooth line. Right? It does not make sense to talk about exact probability values for exact number of outcomes anymore. Now fx equals 1 over sigma square root 2 pi exponential of x minus mu da 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 da. The key things to note here is that the only variables that you need here is mu and sigma, where mu is the mean and sigma is the standard deviation. If you know these two values, you can draw this particular line, or you can calculate this particular line. Now this has been normalized such that the area underneath this curve is 1, right? And this area underneath the curve, notice that one of the key things about probability is that the total sum of probabilities equals to 1, right? Y-axis is probabilities, x-axis is the values, or the values of occurrence. So all of the possible frequencies or of the different values of occurrence, their probabilities should add up to 1. Right? So this normal Gaussian distribution fits the probability requirements. Now there's a shortcut version of the normal distribution. We call it the standard normal distribution, also known as the Z distribution. In this case, we make this assumption that the mean is 0 and the standard deviation is 1. Now if you look at the formula, it simplifies the formula in such a way that now fx equals to 1 over pi of 1 over square root of 2 pi exponential negative x squared. This x here just talks about which point are you trying to plot at the moment. So again, this is the function of this particular curve. Now again, this is derived from the exact same formula as the normal distribution, except where the mean is 0 and the standard deviation is 1. Now, why do we actually do this? Why do we actually come up with a totally new distribution where the only thing that differs is the mean of 0 and standard deviation is 1? It's because in the past, where we did not have computers available, if we wanted to calculate probability values, it was quite difficult to estimate probability values from the original normal distribution formula, which we showed you just now, the one with the mean and the standard deviation values. Why? Because calculating probability values require you to do integration. This is a continuous one, and I said area underneath the curve is 1. So probabilities of values from a particular range between, let's say, here to here, I will have to integrate this particular function from here to here. If you still remember, integration gives you the area underneath the curve, which in this case of a probability distribution gives you the probability of an outcome from here to here. Right? I'll repeat that. If you want to know the probability of a particular outcome occurring from values this to this, you would have to integrate the function from here to here. This is true because this is a theoretical distribution, a theoretical continuous distribution, right? And it's defined by the formula. Now, in the past where there are no computers, it is not easy to do such integration methods. So what did we had? We had tables, just like the log tables you have. So you have distribution probability tables as well. Now the problem with these probability tables is that the integration values you get would differ depending on different means and different standard deviations. And obviously, when you collect different data, they will have different means and different standard deviations. So it was not possible to generate so many varieties of tables just for every single possible collection of mean and standard deviation. So what they came up with is, rather than doing that, you would first collect your data, and then you would normalize your data. You would normalize your distribution to have a mean of 0 and a standard deviation of 1, so that it fits this standard normal distribution. And then this standard distribution would have a table, a lookup table that says that if you want to search between here and here, then the probability is here. And all it does is it has pre-calculated the integration for you. It's pre-calculated the area underneath the curve for you, so that you wouldn't need to do it yourself. You just need to look up the values from a table. So it was just for that and for no other reason. We do not actually need to do this now in the modern era where we have computers. However, since in the exams and whatnot, you cannot bring your computer to you into an exam, you still have to do it with the standard normal distribution way, looking up the table way and so on and so forth. Yes, you no longer have to do it with your computer, but but because of limitations, you're still doing it the old way, right? Now, some other quick rules of thumb. We actually talked about this previously when we first introduced the idea of the normal distribution, and that is the idea of what is the probabilities or the percentages of mean plus minus standard deviations. Now for a normal distribution, remember, this is a theoretical distribution. This is mathematically defined. So the mean plus minus 1 standard deviation, which in this case is just 1, plus minus 1, this area contains around 68%. Plus minus 2 here is 95.5%, or about 95%. And plus minus 3 is almost, is more than 99%, or almost 100%. And just keep in mind, because this is a continuous distribution, this thing goes to infinity and negative infinity. So you could theoretically calculate what was the area all the way up to infinity, right? Now, this is not just true for the standard normal distribution, this is true for all normal distributions. So the mean, if the mean was 5 and my standard deviation was 3, then it would be 5 plus minus 3, and that would be 68% of the area, right? So it's the same thing, just that this is the standard normal distribution, which is a normal distribution that's defined to have a mean of 0 and a standard deviation of 1. And the only reason for doing that is so that we can use these pre-calculated integration tables, these pre-calculated probability tables to do our calculations. So just to point out again, continuous functions have infinitely many possible values, 1.1, 1.001, blah, 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 blah. So it is not possible, this is not a discrete function, so it's not possible for you to ask the question like, what is the probability of x equals 1.1, right? It doesn't make sense. So you cannot use exact values, or you cannot use a single value and look at the height at the frequency curve at that particular value and say that's the probability of the specific value. It doesn't make sense. What you should do is you have to calculate the area. So you always calculate probabilities in terms of ranges. Now these ranges are usually one way, meaning that what is the probability of less than certain value, what's the probability of more than certain value, but you could also have a probability of between 3 to 5, between A to B, and so on and so forth. But the key thing is there is always a range because you're trying to calculate the area. So then, how do we use this standard normal distribution? Now first off, we of course collect the sample data, and after we have the sample data, very important, you plot the histogram of your sample data and you look at your data. You look at the data you've collected and you say, based on the data that I've collected, does it actually look like a normal distribution? Meaning, does it have that bell-shaped curve? If it doesn't look bell-shaped, it looks like a rectangle, then there's no point going any further. There's no point using these methods because it doesn't fit the theoretical distribution. Now remember, this is the theoretical probability distribution. It only makes sense to use it if the data that you have actually fits it, right? Now, assuming it does, assuming you're saying that my sample data does resemble the normal distribution, right? Then I calculate the sample mean and the sample standard deviation. Then I convert the mean and the standard deviation such that the mean becomes 0 and the standard deviation becomes 1, and that's quite straightforward to do. The formula for that you'll come across later. And when I do that, I convert my distribution from the normal distribution to the standard normal distribution, also called as the z distribution. This is known as a z transform, right? Again, is a very standard or straightforward calculation. Basically shifting the distribution and kind of like shrinking the distribution or expanding it depending. Then after that, I look up the value of the particular range, the probability of range I'm interested from the distribution tables. So, an example of usage. Let's say this is the data that I have calculated. Now, this is what I've observed. This is the data that I have collected. This is what I expected, assuming this followed a normal distribution, right? So I could calculate the expected values. Now notice these are all ranges once again. Less than 20, 20 to 22, 22 to 24, and so on and so forth. Here's my mean, here's my standard deviation. What then is the probability of x being greater than 42? What's the probability of me finding, or what's the probability of getting people with this serum level that's greater than 42? Now, I have my mean, I have my standard deviation. I'll just show you what the z transform looks like for now. As mentioned, it's very simple. It's this range which you are targeting, this 42 value, minus of your mean, right? So 42 minus this, divided by the standard deviation. That's it. That's all there is to it. And you get a z value of 1.29. We'll talk about how this thing actually works in the future, but for now, just bear with me. So if we look in the table, the z distribution table, if we look at what is the area underneath the curve for above 1.29, it equals 0.0985. Or in other words, probability of x greater than 42 is about 10%, or 0.1. Now, you can try this yourself. Assume systolic blood pressure in normal healthy individuals is normally distributed with mu 120 and standard deviation as 10 millimeters of mercury, and you can just try this out for yourself. I'll leave that for you, right? Now, just one last thing I'd like to emphasize again. In this case, we are using these values, we are transforming them using the Z transform, and then we're looking up them with tables. Now, if you really wanted to, you do not need to use the Z transform. Knowing the mean and knowing the standard deviation, using the formula of the normal distribution, the fx equals blah 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 blah, mean and standard deviation, you could calculate the area underneath the curve for 130, 140 and so forth by yourself, right? Just using a computer. But we don't do that simply because it is easier if we do not have a computer. And remember, these tables were generated, these practices came about when computers were not so widespread. It is much easier to convert to a standard distribution which is well known and use the pre-calculated values inside there, right? Now obviously it might be more accurate if you do it yourself by computer, but usually we do not need such high accuracy when we come up with our values, right?